So how do we get a sequence with these properties? To get a sequence with these properties, I'm going to use a linear feedback shift register. And here's an example of that. And it's going to be, I think, easier for me to show you an example to get why this works. It kind of looks a little bit like a convolutional encoder, but it's not really the same thing. But we're using the same elements, the same physical devices in order to build our pseudo-noise generator or our PRBS generator. So what's nice about this is that it is very inexpensive components that we can use to build it. Very tight, small. And if we want to run at very high baud rates, it's easier to do because the components are so simple. So what's important to realize in this shift register is that there's the cyclic nature of it that I have. In this case, in this example, there are 4 registers, and I cycle through them. And finally, I get the output. But the output is computed by looking at some linear combination of the registers in order to create the new feedback input. So let's look at an example here. So suppose I initiate these registers at 1, 0, 0, 0. So that's the first state of the registers. It's a finite state machine like we saw with the convolutional codes. And if I look at the input now, what is the output? If these are the states of the registers, what's the output? Well, the output, it's just x4. Whatever is in this last register gets shifted out. So our first output, if we initially set the values here, is going to be a 0. And now we're going to do our first shift. So what happens with our first shift, is that we take x3 and x4 and we do a modulo 2 sum. So here I have 0 and 0. Add them together, I get a 0. So what do? I shift in a 0. So now we'll see at the next timestamp, of course, we have the 0 here. Oop, that's a little hard to see. We have the 0 here, which was the result of this mathematics. Now this was a 1. It gets shifted over to here. And then this 0 gets shifted over here. And then this 0 gets shifted into x4. And sure enough, that's what we read in the next line of this table. And then what is the output at this instant of time? Well, of course, it's just whatever x4 is, I output. And you can see how we continue to do this shifting in. Again, I've got 2 zeros. I'm going to shift in a 0. But eventually, I have at the input a 1 and a 0, and I start shifting in a 1. Of course, we go through this whole thing, and we look here at the output. What is the output sequence that I have generated from this linear feedback shift register example? And we can see that once I get to this point, I get to 0, 0, 0, 1. The next shift is going to give me 1, 0, 0, 0, which is where I started. So once I get to where I started, well, then the output starts repeating because I start from the same state and I chuck through all of them. So we call this the length of the sequence before the sequence starts to repeat itself. And we call this an M sequence. And the M stands for maximal length sequence. So if I start with 4 registers, how long a sequence can I get? You know, in this case, it didn't start repeating until I got all the way down to the initial state. You can look at some other shift register combinations, and it might start repeating at a much shorter length. So this mapping was chosen because it generates one of the maximal length ones. So just as in the case of the convolutional encoders, we had a generating matrix or a generating vector for each one of the code words. Here there's no code words, there's just one vector. It's the interconnections that create the PN sequence. And there have been found certain sequences, certain generating vectors which generate maximum length sequences. So we can look in a table where somebody has computed this and recorded this, what you can do. So M, an M sequence, M is for maximal length. Given M registers in a linear feedback shift register, there are 2 to the M possible states. 0 is not an allowed state. You know, why would I not want a 0 state in my shift? What happens if I put a 0 in here? Well, no matter what the states are, no matter what these interconnections are, if I take a bunch of zeros and I add them, I'm going to get a 0, and then I'm just going to always get 0. So, you know, 0 is not an allowed state. But in any case, theoretically, the maximal length that I could achieve would be 2 to the M minus 1, where I reject the 0. After that, I have counted through all the states, and of course, then it'll start repeating because I get back to the same state. So the M sequences have this property that for M registers, then the length of the sequence generated by this has 2m to the minus 1. Now, I've showed you how to generate this sequence. And now I have to show you, well, maybe I won't show you, but at least I'll tell you, that these sequences, these M sequences, have the properties that we were looking for in a pseudo-noise sequence. So let's check our example to validate that at least in the example we see the properties that we were looking for. So here is my output sequence, and I count how many 1s are there and how many 0s are there. And there are 8 1s and 7 0s. Remember, 2 to the m minus 1 is always odd, and therefore there's never going to be exactly the same number. But with an M sequence, they're always off by just 1. There are no long subsequences of 1s and 0s. In fact, the longest sequence of 1s is always the number of registers. So there's one sequence, and it has 4 1s. That's the longest run of the same number in any sequence. So in any M sequence, there will be one sequence of M 1s, in this case M equal 4. There will be one sequence of M minus 1 zeros. Of course, the 0 state is not allowed, so that one's thrown out. That's why I get M minus 1. And if we go down next, how many sequences are there with length 2? So there's one sequence with length 2 of zeros and one sequence of length 2 of 1s. And then what's left are 4 sequences of length 1. Those are the isolated zeros and 1s. So this is an example, but if you look at the maximal length sequence properties, it will always have this distribution of runs of similar bits together. And we can see that it has a nice distribution where the long ones are really limited and the majority of them are going to be very small runs. So this gives us our second property of no long subsequences. So I want to look at the autocorrelation function for an M sequence. And let's go back to what is the definition of an autocorrelation function. And in this case, it would be the function multiplied by itself with some delay factor, and then I integrate over the total of the whole sequence. And in this case, I have a normalization factor, which is basically the length of the sequence. So here is what happens when there's 0 delay. And when there's 0 delay, then everything adds up. It's like the area under the curve of the square. And if we think of this as sort of zeros and 1s that I'm adding up in the discrete case, then if I have them think of it, I guess instead of logical 0 and 1, it'd be better to think about it as plus and minus 1. That's the best way to figure out what's going on here. So if we're logical 1 and 0 is what I showed you in the table, what I'll be showing you so on here. But think of them in terms of being positive and negative 1s. And that when I do the autocorrelation function, well, I square them. So if it's a 1 or a minus 1, it always comes out to a 1. And I integrate over it. So basically, if I'm talking about discrete bits, in that case, the k factor would just be equal to the length of the sequence. Because the sequence is of length 2m minus 1. And I'll have either plus 1 or minus 1. And when I do the autocorrelation, exactly aligned, the 1s will multiply 1s, the minus 1s will minus 1s, you know, everything will be perfect, and I'll get this result. So now I say, I'm going to use this to normalize my autocorrelation function. And in this case, I'm going to do the exact same operation here, only I'm going to take the function multiplied by a delayed version of itself, and I'm going to integrate over that. And this discrete version that I'm going to show you now, it's really like summing instead of an integration, and I'm going to sum over, you know, all of the elements in the sequence, and when I do that, it will be with the delayed version. When I sum it up, it will be, you know, am I going to multiply a plus 1 with a plus 1, or am I going to multiply a plus 1 with a minus 1? And when I multiply a plus 1 with a plus 1, then I'm going to get a 1, a minus 1, and a plus 1. I'm going to get a minus 1. And so really, if I want to know the result for the binary case, the discrete case, in that case, it's really just going to be the number same minus the number that are different. Because when they're the same, it's going to be 1, and when they're different, it's going to be a negative 1. So this makes it very easy for me to calculate the autocorrelation function. So now I'm going to take this definition. I'm going to use this normalization factor, and I want to calculate what does the autocorrelation function look like for this maximal length sequence, this pseudo-noise sequence. So we'll be looking at the autocorrelation of M sequences, but for the discrete time case. So I've taken the sequences here, and I've created, I think it's an Excel file, where I have the sequence that we wrote, and I just repeated it here. And I think we can see 1, 1, 0, 0. It repeats here 1, 1, 0, 0. So you can see that there's a delay between these two copies of the same sequence, a delay of 2. So I wrote over here that the delay is 2. And I've done a couple delays. Here's 4, 7, and I think I have another one down below. But in any case, what I'd like to do is calculate for each one of the delays what is the correlation between the delayed version and the original version. And so this is the plot that I'm going to be generating. This is a plot of the autocorrelation function, and the x-axis is the delay. And so for instance, for setting 4, when they're delayed and they're 4 shifted from one another, I'm going to add up how many times are they the same, how many times are they different, and that difference gives me the autocorrelation value for that particular delay. So for instance here, 0, 0, that's the same, same, now this is different, the same, etc. And if I add all these up, I'll find that there are 7 the same and 8 that are different. So remember, I have that summation, and I said that the autocorrelation was going to be the number, was going to be equal to the number that are the same minus the number different. So that's going to be 7 minus 8, or minus 1. But then I said there was going to be this normalization factor that's going to be 1 over the length. In this case, it's 15. So when they all line up, I'm going to get 1. I'm going to get 15 divided by 15. That's going to give me 1. That's going to be my peak there. But all of the other ones, this great property of this maximal length sequence is, for all the other shifted versions of itself, I'm going to get -1 divided by 15, a very small negative number. So this is a plot So this is a plot of that autocorrelation function. And what I have is the delay versus the correlation. And this first, all these x's represent the discrete value that we calculated. And if I wanted to go through the continuous time, very simple to get the rest of this plot here. So the normalization is that the peak occurs at 1 and that the autocorrelation for all shifted delays is -1 over p, where p is the length of the sequence. So why do we look at this? Because this becomes a very peaked autocorrelation function. It has a very sharp peak. Remember, we wanted it to be a delta function, and it looks pretty good to be like a delta function. So why did we get this properties? Because for 0 delay, of course, all of the bits are identical, and the spike has a height. If we didn't normalize it, the height would be the code length. For any other delay, half the bits are identical, and the other half are not, and so this is odd and even number, so of course it's always off by 1. So the autocorrelation is very small. And what's interesting is if I want to make it more like a delta function, more peaked, the only thing I have to do is change the code length, because this is always fixed, right? It's always, the difference is always going to be 1. It's the characteristics of the M sequence. There's going to be, like 1 more different than the same. And if we didn't do the normalization, maybe I shouldn't have done the normalization. Maybe it's easier to see there. If this is at -1, then this height is always going to be the length of the sequence. And the longer the sequence is, the more of a peak I have, and the more noise-like the sequence is. So autocorrelation and synchronization, they go hand in hand. The sharper the autocorrelation, the more easily we solve our synchronization requirement, which is why these PN sequences are so crucial experimentally. Now, you'll see in the textbook, they talk about another application for PN sequences, which is spread spectrum technology. And it's interesting, you're welcome to discuss it, but for us, it's really the synchronization that brings it into play, especially in your equalization project. I'll just mention that for that application you'll see in the textbook, you have to do the synchronization in hardware. And so there's many different ways that you can do the synchronization, and it's kind of interesting to see the different approaches. One way is to do what they call a sliding correlator. So you actually just try, the data comes in, and you slide over it gently, one by one, until you find what is the peak, and then you have good synchronization. There are some parallel, instead of waiting, it's slow though to get your synchronization, because you're stepping through one at a time all the possible positions, and so there is a more parallel approach to doing this in hardware. And there's another parallel search, etc. But what I want to mention to you is that our requirement is not this hardware requirement. We're doing offline synchronization in our experiments. I might say that in a bit error rate tester, they might have this hardware in order to do a very fast synchronization, make things speedier. But in our example, we're doing offline manipulation of our captured signal. And if it's not an if implementation is not an issue, how would we do it? So in MATLAB, we can do this synchronization by simply using a convolution command. So you convolve your received signal with the transmitted PRBS. And when you line up, you will get a peak when you have, that will tell you at which point the beginning of the sequence is in your data. So I want you to practice this with the equalization assignment. We'll be giving you the code that has it. This is how you count errors. Because if I send you a whole bunch of ones and zeros, which are a PRBS signal. And you have to know, well, this is the beginning of my PRBS, and I know, like maybe this is my PRBS recorded, I know what was sent. This is my received data. But my received data, every now and then, of course, I'm going to have an error in the received data. And when I have an error in the received data, it's not going to exactly match up because this will be a 1 instead of a 0. But because the autocorrelation function is so peaked, I'm still going to make it very obvious when I get the right synchronization. So I encourage you to have a look at it, and some of the assignment will be to identify what's going on in the code so that you can use the PRBS in order to estimate the bit error rate.